let's see. Wednesdays. Man, I was like this last Wednesday. This Wednesday too. Just not the best day. Let's see. I've gotten a few questions about allylic halogenation, and I wanted to talk about that briefly. So, for example, I want to go over this problem where we take this substrate right here and we treat it with NBS and some lime. Okay, so we should recognize we're going to undergo allylic halogenation. So really this ends up being kind of like a two-step problem. And so I asked this problem one way, and Sapling actually asked it a little bit different. So I wanted to clarify for the Sapling one where it and I disagreed. So for example, we've got a pi bond, and so next to that pi bond we've got a couple of protons, right? We've got the red proton and we've got the blue proton, and so those are certainly going to give us the most stable radical. So if we abstract the red proton, that's going to put a dot at this position. And so this dot is going to be resonance stabilized such that we can also put a dot at this position. So we've got a couple of contributors here. Now, how many radicals is this picture indicating? How many radicals are in red here? Just one, right? Because we're looking at resonance structure. So these aren't multiple radicals, it's just two different contributors, two resonance contributors to one radical. So here we've got our red radical. We could also abstract the blue proton. So in that case, we get this blue radical. Now, the difference, the key difference between the blue radical and the red radical are going to be that here we've got a tertiary contributor. Where up here we don't have any tertiary. So what's going to be more stable, red or blue? Definitely blue, and that's based on the fact that now we have a very stable resonance contributor. So once or at least the way that I ask this question, once we've picked out our most stable radical, that's the only radical that I think we should consider, right? And that's because even just by choosing one radical, we end up with a complicated mix of products, because this one radical, which is resonance stabilized, so it's got radical characteristic at this tertiary carbon, it's also got a carbon with radical characteristic at the secondary carbon. And so we can have reactivity at either of those carbons. Which is the more important contributor, the one on the left or the right? Definitely the one on the left, right? Because this is the more stable radical one. So when we talk about major products, I'm asking you, well, basically, of these resonance contributors, which carbon has the most radical characteristic? And so since this is the more important contributor, our major product is going to be the reaction of bromine at that tertiary center. So we have our bromine, which can attack from the front, plus the diastereomer, where the bromine can attack from the back. But we don't want to forget the fact that we have a resonance contributor where we have a secondary radical, and so it's not as important. So we'll still form some of that product, but in this case it's going to be the minor product. And so now we have our bromine attached there, both from the front as well as the back, for plus diastereomer. I got a couple of questions before class. I think there's a Sapling problem that actually wants you to list all of the possible products that could result from an allylic halogenation. And so in that case, I'm calling this major and minor. In reality, some of this might form a little bit, but I don't worry about that in class. I just want everyone to know that Sapling might actually expect you to figure out the products that could come from that as well. So just a heads up on that. So it's a two-step. On an exam, it's basically going to be a two-step problem. What's the most stable radical? And then number two, what products can form from that most stable radical? And so we can see, just considering one of them, we have multiple products that can form. All right. So last time, we had just finished up SN2 reactions. And so I think, yeah, we put our label for Roman numeral 4, which is our stepwise mechanism. So that's where we're going to start back into it today. I guess I'm going to relabel. So we've got our stepwise mechanism. And of course, the name of that mechanism is SN1. All right, so just like with SN2, we started with the letter A. We'll do, well, I guess every section we start with the letter A. But also the title's the same, and so that's going to be kinetics. All right, so for kinetics, what we're going to have is some electrophile. And so in this case, we'll just have a secondary electrophile. And so we can see it's attached to a leaving group. So the thing that's different between SN2 and SN1 reactions is the timing. It's all about the timing, and I've talked about that a little bit. And so in this case, This is sort of like, imagine you're at home and you're waiting to be picked up by a date. Now you're the electrophile, and the nucleophile is the date. It's the nucleophile is going to come by in its new, I don't know, Honda or Prius or I don't know, some really cool car like that. And so you're waiting, and he never shows up, but you're like, hell, I don't care. I'm all dolled up. I'm still going out. And so that's what you do. You've waited long enough. So you have waited and waited and waited, and he never came by, and you're just done with it. You still want to hit the club, and so you do so. You go ahead and kick that leaving group off, even though the nucleophile is not there to help. You're gonna do it anyway. And so what we're gonna end up is this intermediate. Now, this is not the best intermediate in the world. It's a carbocation, and that's why you waited so long. It's because, well, if we're gonna form a carbocation intermediate, we're gonna have to form a very unstable intermediate that's high in energy, and that's not very ideal. So it's slow. It's a slow process to form our carbocation. So you're at the club, and the music's blaring, and you eye that nucleophile, in the corner of your eye. And so attraction occurs as it once did when you first met. And so our nucleophile immediately sees you, walks over. And that's going to be a pretty fast process because now you've overcome the activation energy, right? You got it. And so what we end up with is the same exact product as in the SN2 reaction, but we just got there differently. You didn't get picked up. Instead, you took yourself. All right, now let's think about those two steps. So in an SN2 reaction, we saw that it's a concerted mechanism, it's just one step. In an SN1 reaction, we're seeing that it's two steps. That's kind of backwards, right? Don't let that confuse you. So an SN1 is two steps, and an SN2 is one step. And so it's easy to get those kind of mismatch in your mind. We're going to talk about why we end up with the SN1 name here in a sec. Which step, this first or this second step, do you think is going to take the longest? Yeah, it's going to be a whole lot easier to form a carbocation than it is for this carbocation to go on and react with a nucleophile. And so what that means is that our rate determining step is going to be this first one. And that's kind of the important thing about the SN1 reaction, as we'll see. All right, so when we think about the rate determining step of an SN1 reaction, actually, let's go back to SN2. What was involved in the rate determining step of an SN2 reaction? Was the nucleophile involved? Yes. Was the electrophile involved? Everything was involved because it's a one-step reaction, right? So everything that's kind of having any business in the reaction is going to be taking part. But that's not the case because in an SN1 reaction, because when we look and we can see that rate determining step, is just the leaving group leaving on its own. Is the nucleophile anywhere around that first step? It's not. So that's the big key difference between the SN2 and the SN1. So in this case, we see that only the electrophile is involved in the rate determining step of SN1. Okay, so when we write a rate law for an SN1 reaction, we're going to say the rate is equal to K. What's K? Yeah, so that's just the rate constant. We don't care about the number. We just, in this case, it exists. We have a K. And so when we write the molecules that are involved, all right, so we're going to have our electrophile, but our nucleophile is nowhere to be seen. So instead of having two things, in this case, we've only got one. Now, we called it an SN2 reaction. We called it a bimolecular process. What do you think we call this process? That is unimolecular. And so when we go to give this thing a name, what we have is SN1, where S means substitution, N means nucleophilic, and then 1 is going to come from that unimolecular. So that's how we have SN1 and SN2. It's all about how many things are involved in that rate determining step, and ultimately we'll see that there are pretty big differences between the two. All right, so letter B, stereochemistry. By the way, did you know that in 3 weeks we will be done with Orgo 1? It's going to be in our past. I'm pretty excited about it. I don't know about you guys. I'm actually pretty excited about this. May is going to be awesome. Okay, So, of course, I guess I don't have other exams and things to take after our exam. But I do have to grade our exam, so I mean, I'm not done, but it's also not that high pressure for me. But keep in mind, I have been through it. All right. Literally well, not literally, but very close to actually being in your shoes since I was a student here. All right, so we're going to start with a substrate here. We're going to learn through example. And so, do we have a chiral center? Yeah, we definitely have a chiral center. We've got 4 different things. So let's see. Let's determine this stereochemistry. 1, 2, 3, 4. Is that going to be R or S? Yeah, so it's going to be S. If we put our thumb in the back, we're able to rotate with our left hand. 1, 2, 3. And so we have an S stereocenter here. And so we've seen that the first step of this mechanism is basically going to be the bromine going off and doing its own thing. And so that's what we're going to start with. And so in this case, we're going to be forming a carbocation. Now, a carbocation has what hybridization? It is sp2. And so what kind of geometry does it take? It's trigonal planar, right? We're going to end up with a planar structure. So that's what we've got to make sure that we draw. So when we draw this, we're going to have our ethyl, which is moved straight up and down. So basically, everything's going to be straight up and down. So our propyl group will also be straight up and down, except on a wedge. And so our methyl will be straight up and down, except now on a dash. So we've got a trigonal plane, and that trigonal plane is basically like my hand right here. Okay. So that means we have some leftover p orbitals because this is going to be an sp2 hybridized carbocation. And so now we can think about the consequences of reacting this carbocation with an incoming nucleophile. And so in this case, we're going to use chloride to be our nucleophile. So with an SN2 reaction, we talked about front side attack versus back side attack. Which do we always follow with an SN2? Always do backside attack. But since we're going through a new mechanism now where our bromine is out of the way, we don't have to worry about conflicting with our bromine anymore. Can we attack the right side of this molecule with our chlorine? Yeah, it's just as likely as attacking the left side. And so now we've got 2 possibilities which are totally fair. All right, so first off, we could attack this p orbital, and so this would technically be a front side attack because that's where our bromine was. And then we have the other possibility where we can attack the other side, and so that's going to give us our backside attack. All right, so let's see what products form between our front side and our back. So let's do our, let's do our backside attack first. And so that's basically going to give us that same inversion product that we saw from the SN2 reaction, right? Because if our backside attack attacks from we end up with our nucleophile on the left side, we're going to have our chlorine. And so everything's going to be pushed over to the right side, just like we saw in the SN2. And so now we have our propyl on a wedge and our methyl on a dash. And so let's see, 1, 2, 3, 4. So what's that stereocenter? Yeah, so we've got 4 in the back, and we can count 1, 2, 3 clockwise, right? So that's an R. And so furthermore, this is going to be our inversion product. And it's our inversion product not because we changed S to R, right? It's our inversion product because mechanistically what happens to our 3 bystanding substituents is they're starting on the left and they end up on the right. And so we've inverted them from the left side to the right side through a backside attack. We can also have our product that results from the front side attack. And so in that case, our chlorine will be on the left. And it's really kind of a roller coaster ride for our bystanding substituents in this case because they start out over here on the left side and we form a carbocation, and so they switch into the middle. And then we see the front side attack, so they get pushed back to the left, right? And so they end up basically where they started. And so if we've got an inversion product that is R, what must this stereocenter be? S, right? And you should be able to clearly see that those are mirror images of each other. So we've got S. And so furthermore, we no longer have our inversion product. We're going to refer to this as our retention product. And so taken together, we're going to end up with a racemic mixture. Was our starting material optically active? Yeah, it was, right? It was chiral. Are our products together optically active? No. They're not, right? We basically wiped out that optical activity because by going through an SN1 mechanism, we end up with a racemic mixture, and so those are going to cancel each other out. All right, just another reminder. We see here that the inversion product, we start with S and we end up with an inversion product of R. Is that always going to be the case? No, because it's going to depend on the incoming priority of that nucleophile and whatever the priority of our leaving group was. So sometimes it'll switch to R. Sometimes you're going to see an inversion product where it's still S, right? And then other cases you can see where you have the retention product that changes to R. So whatever you do, always, always just reevaluate, reprioritize our substituents, and then determine RS stereochemistry after the reaction's done. All right, so SN1 reactions can become a little messier, and that's no good. Boo. All right. All right, next up's the fun stuff, the fun thermodynamic stuff. All right, so there's going to be letter C. Structure versus rate. Now, what aspect of the structure in an SN2 reaction is most important? There's crowdedness, right? And so the more crowded we have an electrophile, the slower we're going to have a reaction. Yeah. And so the inversion product, it comes from the fact that basically that would be the same exact product that we got if we went through an SN2 reaction, right? Because we've got our three substituents over here on the left side, and so they end up in the product on the right side. They've been pushed over, they've been inverted to the other side just like in an SN2 reaction. So we can call it the inversion product because ultimately the product compared to the starting material is inverted, right? It just doesn't go through a mechanism where the nucleophile is pushing them the whole time. And so we can have both cases. In the backside attack, we end up with the inversion product. If we go through a frontside attack, we push those substituents right back to the left side. And so we've retained the initial orientation, and so we call that our retention product. All right. So structure versus rate in an SN2 reaction we learned is dependent on crowdedness. What aspect of the structure in an SN1 mechanism is you think, going to determine the rate? Well, what's the high energy intermediate that we form? It's a carbocation, right? And so we've learned that there can be different carbocations, favorable versus unfavorable carbocations, and in fact, that's going to be the important decider when we talk about the rate of an SN1 reaction. So we'll say that the rate determining step involves formation of a carbocation, C+. All right, so if we're going to draw an energy diagram for an SN1 reaction, we'd have energy, reaction progression. How many intermediates are there in an SN2 reaction? There's no intermediates, right? Because it's just one step. We never have any valleys between mountains because we never have any mountains except for the one, right? The first step that gets us from starting material to product. All right, so we have a two-step reaction now, which means in an SN1, how many intermediates will there be? There's going to be one, right? So that's the carbocation in question. So the reaction diagram, or the energy diagram in this case, all right, so there's our rate determining step. That's going to be our highest point on our path because it's the hardest to form. And then from there, we'll have a little hump, and that'll go down to product. So we have starting material, product, and carbocation intermediate. And so this gap right here between our highest energy point is going to be our activation energy, and also, since it's the highest, is going to be the rate determining step. All right, so because the rate determining step involves the formation of a carbocation, it's going to be the stability of that carbocation that determines reaction rate. All right, so again, we're just like last time, we're going to do this considering an example. So we'll say consider We have some alkyl bromide, and so we'll just say that's a generic alkyl bromide, so that's RBr. So what we're going to do is we're going to react to that, in this case, with water. All right, so we'll have alkyl bromide plus H2O, and so what we're going to end up with as a product is going to be an alcohol, plus, I guess here, we're going to have some HBr. Now let's think about this. If we add water to a carbocation, what do we get? We should end up with something that looks like that. But we always want to make sure we get to a neutral product, right? And so how are we going to get to a neutral product from that? We've got to deprotonate. So specifically with SN1 reactions, it's fairly common to add something which is going to have too many bonds, and so then we need to go through an extra deprotonation step to form our neutral product. So in this case, you can just take some base if you're drawing out the mechanism, undergo a deprotonation, and so that will lead you right to your alcohol product plus an HB of some kind. All right, so it will be sometimes necessary to undergo a proton transfer step. We'll talk about that again in just a second. All right, so we'll draw another table like we did for the SN2 reaction. And so we're going to use the same alkyl bromide. So we've got, let's see, methyl bromide. We've got a primary bromide, a secondary, and a tertiary. And so we'll again remind ourselves of the type. So we've got a methyl, a primary, a secondary, and a tertiary. Now let's think about that. Let's think about that as it pertains to carbocation stability. What's going to give us the most stable carbocation? Is it going to be a methyl carbocation or a tertiary? Definitely tertiary, right? So here we've got our most stable C+, and up top we've got our least stable C+. And so that's basically what's going to determine how fast our reaction goes. So when we can finally compare rates, we'll say that our relative rates, what do you think is going to be fastest, the top or the bottom of this chart? Definitely the bottom, because that's going to go through the most stable intermediate. And so we end up with some big numbers. All right, so for relative rate, our tertiary is going to be about 103,448. I really question the precision of that number. That seems oddly specific. All right, so I'm just going to say it's in that ballpark. The secondary is 1. And so we can see there's a massive difference between the tertiary and the secondary in terms of relative rate. When we talk about the methyl and primary, we don't even see it happen, so we say that that's not detected. It does happen at some rate, but it's so slow that we just never even see it happen, so it's pretty much we can say it doesn't. Okay. So why is this the case? Ultimately, if we compared an energy diagram for the secondary versus the tertiary, what we would find, all right, so I'll say energy, reaction progression, we'll have the same starting material, same product. We'll color code our secondary as red, and our tertiary is blue. And so what's going to be more stable, the tertiary or the secondary? Definitely the tertiary, so that goes lower in energy, so we'll put that, say, right here. So that's going to be our tertiary C+. And so its pathway is going to look sort of like this, versus our secondary, which will make red. So its pathway has a much higher rate determining step, and so ultimately ends up being way, 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 way slower, and it's because of that difference in stability of carbocations. So here, we've got the rate determining step of our secondary. Here we've got the rate determining step of our tertiary. All right, so tertiary is way faster because that rate determining step is much lower in energy. Let's see, we're going to summarize these trends that we've seen in SN2 and SN1, but first off, we've got to add a letter. All right, so our letter that we're going to add, we didn't do this for SN2, so we're just going to call this D, and we'll call it uh-oh. because there's other stuff that goes on with SN1, and ultimately it's not ideal. It's some complications. So we'll just, complications. All right. So let's think about an example. Let's say we've got this secondary chloride. And so we've seen thus far that a secondary alkyl halide can undergo both SN1 and SN2. So what we're going to do is we're going to react it with ETOH. What is ETOH? It's ethanol. So we're going to react it with ethanol, and furthermore, I'm going to go ahead and just tell you that this is going to go through an SN1 type mechanism. Now, all things being equal, we might expect basically the chlorine to be swapped out for the ethanol, right? And so in that case, what we would find is a product that looks like this. However, we do this reaction in the lab because, I don't know, we're bored. And so what we end up seeing is this product right here also forms, which is a little interesting. And so furthermore, what we find is this is actually our major product, while over here, this is our minor product. So it's actually more favorable for this to form. And so what we've got to think about is how on earth can we get from this starting material to the major product that we're seeing form in our reaction. All right, so anytime that you might feel a little lost, let's say I ask you to draw a reaction mechanism and you're not sure exactly how this happens, do what you know. And so I've told you this is an SN1 mechanism, so what's the first step definitely going to be? Yeah, we're going to eject our chlorine, right? And so what we have is, since it's an SN1 mechanism, we know just automatically that's the first step. So what that's going to lead to is a carbocation, and specifically it's going to lead to this carbocation right here, which is a secondary carbocation. And so we can imagine from here reacting with our ethanol to lead us to our minor product, right? That makes total sense. We're just snapping our nucleophile in to this point. We'll have to do a proton transfer, but ultimately we end up with our minor product. But that of course, is not our major product. And so who can think of a way that we might be able to essentially get to our major product? What is it? Yes, so it's a 1-2 positive. And so we talked about 1-2 shifts, right? And this is why carbocations are pretty much unfortunate, is because other things can go on. So we learned a while back when we were doing electrophilic additions that 1-2 hydride shifts, 1-2 alkyl shifts are totally possible. And so in this case, what kind of shift are we going to want to do to, I guess, make this tertiary carbon our reactive center? Yeah, we're going to want to undergo a 1-2 methyl shift. And so what that's going to look like is we'll start our arrow where? At electrons. I promise someone's going to start an arrow not at electrons. All right, and so in doing so, we're going to have a 1-2 methyl shift. So that's going to lead us to a new carbocation intermediate that looks like this. All right, so what kind of carbocation is that? That's a tertiary. And so is this thermodynamically favorable? Is there a good reason for this to happen? Yeah, if we can form a more stable carbocation, that's what we're going to do. And ultimately, that's why we see this end up as the major product. So from here, we can react that with our ethanol. And so this one step that I'm showing, is that going to lead us to the product? Keep in mind our oxygen's already making 2 bonds right here, right? And so by connecting it via this red arrow, it's now going to make 3 bonds and it will have a positive charge. So we can't deprotonate in the same step. So what we've got to do is show the product of this step, which is going to be a positively charged oxygen. And so then how do we get from that cation to our product? Yeah, so we could, let's see, so we don't have water, but you could use a generic base. In this case, we could use our ethanol if we wanted to. And so here we will deprotonate and then end up with our final product. Okay, so complications can arise whenever we have SN1 reactions, and so honestly, it's typically ideal to go for SN2 reactions if possible. Furthermore, SN2 reactions are more stereoselective. We only get inversion products. So much more valuable. Let's say that SN1 often undergoes one-two shifts, and then we'll also say that it often undergoes proton transfers. Are we ever going to see any 1-2 shifts in an SN2 reaction? Never, because we don't form a carbocation in an SN2 reaction, so it's only an SN1 reaction that we'll see a 1-2 shift take place. But sometimes it's possible to see a proton transfer in an SN2, and so this isn't just in SN1s. We'll say SN2 can as well. And so an example of that, we could take, say, a primary bromide, react it with water, and so we would do our concerted mechanism, but our concerted mechanism is not going to get us to a neutral product. And so we end up needing to deprotonate to get to our alcohol. Certainly proton transfers are more common in SN1 reactions, but they're also possible in SN2 reactions as well. Specifically with, say, water and alcohols, when they're involved, you'll often see a proton transfer. All right, so let's go ahead and summarize what we've learned thus far. And so electrophiles, all right, so we get a reaction and we see that there's a potential electrophile. One thing we want to make sure is that our electrophile contains an sp3 carbon leaving group bond. All right, so no matter what we do, we have to look for an sp3 hybridized carbon, and it needs to be connected to a leaving group for us to undergo substitution. All right, so let's see. We've talked about 4 different possibilities in terms of our electrophile structure. So we've seen a methyl, we've seen a primary, a secondary, and a tertiary. And so we've talked about some trends between these things. All right, so one trend that we talked about was crowdedness. All right, and so where does crowdedness increase? Left to right or right to left? Definitely left to right? So a tertiary alkyl halide is going to be much more crowded than a methyl alkyl halide. And so let's think back to SN2 reactions. What's more favored in an SN2 reaction, an uncrowded methyl or a very crowded tertiary? Methyl, right. And so here we can say that we favor SN2. And that means, what do you guys, is it disfavor or unfavor? I thought it was disfavor, but 10 o'clock and I fought about it for like a minute. So. So we don't know. Is that? I'll go disfavor. I'll use unfavor below, and you guys can pick out whichever you like. So now we'll say that this disfavors SN2. So we're much more likely to see an SN2 reaction in case where we have an uncrowded alkyl halide substrate. The other trend that we've talked about now that determines the rate of our reaction is our carbocation stability. And so as carbocation stability, well, I guess I gave it away. The carbocation stability is going to increase as well as we go left to right. So let's think about how that impacts an SN1 reaction. Is an SN1 reaction going to be favored or disfavored when we have a tertiary alkyl halide? Very much favored, right? So here we'll say that we are favoring an SN1 reaction, which means on the other end we're going to unfavor it. All right, so on the other end we're going to unfavor an SN1 reaction. And so ultimately when we think about the trends going on, do these go hand in hand? Can we basically easily find where an SN2 reaction is going to be favored versus an SN1 reaction? Yeah, you look at either end. So think about a tertiary. What's definitely going to be favored, SN1 or SN2? SN1. And so we look at this end with the methyl, and we can see clearly that the SN2 is going to be favored much, much, much more than an SN1. All right. Yeah?
Crowdedness has an ion.
What's that?
Crowdedness has an E in it.
Okay, let me fix that. Crowd. We'll even point out my crowd. Is that good?
Yeah.
Okay, crowdedness. Man, my eval, I feel like my evals are going to have so many, like, why can't this guy spell? What is wrong with, did he actually go to school? All right. Let's see. So let's talk about, let's continue, yeah, we've got time to do this. Let's think about why this ends up being the case. So in the case of what we'll learn, let's see. Think about how I want to do this. All right, so what we find is that with a methyl or a primary substrate, we've got two possibilities. We can consider SN2, we can consider SN1. And so what we want to show is an energy diagram. This will be our SN2 energy diagram. This will be our SN1 energy diagram. And so we have starting material, and we have product. And so we're going to make those the same. Ultimately, when we have a methyl or a primary, we find that for an SN2 reaction, it's very uncrowded, which means this is going to be a fast reaction. We have a low rate determining step. And so we're going to end up with a reaction that looks kind of like this. All right, however, when we talk SN1, we know we have to go through a carbocation. And so when we have a methyl or a primary alkyl halide, we're going to have a very unstable carbocation, which is going to be very high in energy. And so this will be, say, up here. So the two possible pathways, SN2 versus SN1, we're going to determine which predominates based on the activation energy. And so when we compare the differences between the activation energy of an SN2 versus an SN1 with a very uncrowded substrate, what's favored? SN2 is very much favored, right? Because we know that in this case, we have a very high energy carbocation in our SN1 reaction. And so we see if these reactions, if we have two possible pathways, we see that the SN2 is certainly favored. We can do the same thing for tertiary. And so in a tertiary case, what we find is, again, we'll say this is our SN2. This is our SN1. And so in a tertiary case, we have a very crowded transition state for the SN2 reaction, which is going to make that very high in energy. So what we find is the new step is going to be way up here. Whereas a tertiary carbocation is pretty stable. Not the most stable thing in the world, but stable enough that it does occur. And so what we find is now it's going to be a lot lower in energy, say about right there. And so the pathway to take an SN1 reaction is about at this energy level. And so when we compare the rate determining step between these two, which is favored? It definitely takes a lot less energy to undergo the SN1 reaction when we have a tertiary substrate. And so here we have a case where SN1 is very much favored. All right, so let's see. We finally have to get to secondary. And so for a secondary, we can do the same thing, but we're going to find that our picture isn't quite as clear as we might hope it to be. And so we have starting material, product, and again, we'll say SN2, SN1. And so what we see is now, for the SN2 reaction, we have a pathway that looks about like this. And for the SN1 reaction, we're going to have a pathway that looks about like this. And so we compare these energy levels, and it turns out they're pretty much the same. And so what that tells us is that in the case of a secondary, we can't just think about what type of carbon we've got, because energetically, we're going to find that they're very, very similar. And so we can say that neither SN1 or SN2 is favored. And so what that means is we're going to have to take some other things into consideration. And those other things are basically going to be the rest of the week in Orgo 1. So we're going to talk about a lot of things that we need to take into consideration to determine when we have a secondary electrophile, what kind of mechanism will we follow. Okay, so let's go ahead and say that we have a key point. And so our key point is we have a methyl, a primary, a secondary, and a tertiary. And so if we see tertiary, you're going to want to think SN1. It's going to go SN1 pretty much all the time in this class. If we see methyl, it's going to go SN2 pretty much all the time. Same thing for primary. Almost always will go SN2. But then we get to the case of the secondary, and so now what we find is more info is needed. And so that's a lot of what this next lecture or so we'll talk about. Okay, so more info needed, and so that'll lead us into Roman numeral number 5, which we'll title more info. All right, so you need more info, and this is where you get it. So this is going to walk us kind of through the process of what else can we consider to determine if we're going to go SN1 or SN2. And it's certainly, I can promise you, at several points on exam 3, I'm going to show you a reaction. I'm going to ask you, all right, do you expect this to go SN2, or do you think an SN1 mechanism would operate? I could ask you directly that, or I could ask you to draw the products that would occur. And so if we have an SN2 reaction, we know we would just see the inversion product, right? If we have an SN1 reaction, we know that we would obtain both the inversion product as well as the retention product. So this is going to be and honestly, this is a pretty canonical piece of Orgo 1, is determining, hey, is it SN2, is it SN1? All right, so more info, we'll say letter A. So the first thing you always want to do, you always determine the nature of the electrophile, which we just spent about 10 minutes talking about, but we're going to spend another 30 seconds just to make sure we're clear on it. So anytime we see methyl or primary, your brain should be in SN2 mode. Anytime you see tertiary, it should be in SN1 mode. And if you see a secondary, well, in that case, we can go SN1 or SN2. We don't have enough information to make that call yet. So the next thing we'll do, we'll title B, electrophile structure. And we'll call this, we'll say extra stuff. There's extra stuff that we consider about that structure of the electrophile, which can lead us down one pathway or another. All right, so I've been saying if it's a primary substrate, we're always going to go SN2. That's not totally the case. And so let's make a list of all possibilities where we're going to have to make a decision. We're going to have to make a call where it's not clear if it's SN1 or SN2. So we'll say that we'll make a list of electrophiles that can undergo both SN2 and SN1. And so the most obvious case is going to be secondary electrophiles. So for example, we can have, say, this cyclohexyl bromide, and so we can see that the bromine, and I've had a couple of questions. So why do we call this a secondary halide? You always want to look at just whatever the carbon is that's connected to the halogen, right? So in this case, we see that it's connected to this position, and this is a secondary carbon. So that's how we determine methyl, primary, secondary, tertiary. Look specifically for the carbon that's attached to our halogen, and that'll tell you. All right, so certainly we have a secondary that's going to require a decision, but we're also going to find that things like allylic halides will also require a little bit of thinking. And so in this case, we can have, say, this, which can undergo both SN1 or SN2. Now first off, what kind of carbon is this? Or what kind of electrophile? It's a primary, right? And so initially we've been saying, all right, it's a primary. We're only going to undergo SN2 because the carbocation that it would go through in an SN1 is going to be too high energy. Well, let's think about that for a second. So if this leaves, what we're going to end up with is a carbocation that looks like that. And so what else can we draw that would explain the extreme stability of this carbocation? Yeah, and so what we've got is a resonance structure that will lead to this carbocation. And so ultimately, we see that this is a resonance stabilized carbocation. So anytime we have a resonance stabilized primary carbocation, it could go SN2 or SN1. And so another example of that would be a benzylic halide. And so in a benzylic halide, what we have is we're basically going to have a halogen that's one atom away from a benzene ring. And so if we undergo this process, what we'll end up with is a structure that looks like that. And so can that be resonance stabilized? Most certainly, right? So we could say this structure is a possibility. And so ultimately, there's going to be two more structures. And so again, we find that we have a primary alkyl halide, but because we're next to some pi bonds, and in this case it's a full benzene ring, it's going to be a particularly stable benzylic halide or carbocation. And so again, SN1 or SN2 can be possible. Let's ask ourselves, what about this structure? So do you think we'd go SN1 or SN2 with this halide? So first off, what kind of carbon is it? So we've got a primary carbon there, which would initially make us think SN2. But importantly, is this an sp3 hybridized, or do we contain an sp3 hybridized carbon-leaving group bond? No, because the hybridization of this carbon is in fact sp2. And so because it's sp2, neither SN2 or SN1 can take place. So what that means is that you're going to have to be able to tell the difference between this structure right here and this structure right here, right? So this is an allylic halide, and so we can see the chlorine is connected to an sp3 hybridized carbon. Here we've got a vinylic halide, and so it's actually connected directly to the pi bond, so we don't have the requisite bond necessary to do substitution, and so we wouldn't actually see anything take place. Same goes for an aryl halide, which looks like this. And again, what we're connected to is an sp2 hybridized carbon. So again, we would say neither SN2 or SN1. All right, let me talk for about 30 seconds. So we're going to continue this stuff. Well, we're going to be definitely done with substitution by the time exam 3 rolls around. So in 3 weeks, we'll be done with class, and things are going to get really, really, really hectic in the last few weeks. So I'm a little concerned that I'm not going to be able to put out enough custom problems for everyone, at least in terms of volume, because I'm going to be very busy with writing exams and things. And so what I'm going to have to do, I think, is turn back to the textbook a little bit and put some problems out. I've already done that for spectroscopy. So I put some IR problems and some NMR problems on Blackboard that I think would be a really good idea for you to take a look at for next week's exam. And then I'm going to do the same thing with substitution problems today. And that way I can basically try to give you the contact you need and not be bogged down in making homeworks. Workshop tonight, 4 to 6. I got to go to the doctor this afternoon. I should be back by 4, but I'll let you know by email if I'm going to be a little bit late.